Okay? So how many nodes do we have there? We definitely have one node here, one node here. There's a nodal plane here between these guys, and there's a nodal plane here. So this is 4 nodes. Okay? 4 nodes. And another configuration. So these are kind of like brain teasers once you get into this stuff. You'll be like thinking, how many different ways can I arrange orbitals? And these guys here, again, 4 nodes, okay, on this. There's a node here, there's a node here, there's a node here, and a node here, okay? So 4 nodes. So again, we'd say definitely there's more anti-bonding character. Definitely higher in energy, right? So we've gone from, so we're at 4 nodes. We start out 0 nodes, 2 nodes, 4 nodes, and then the top of the energy diagram here. And I'll try to do it as big as I can. Every bond is out of phase with every orbital is out of phase with its neighbor, okay? So how many nodes does that have? 6 nodes. 6 nodes, 100% anti-bonding. Okay? This is 100% pi star. Oops, somehow those guys translated. I don't know if I can bring them back so easy. So don't clap yet. It's very difficult to move these critters. Oh, it's going to move those. God. It's a little kludgy. You know, they try hard when they make these software things. Yeah, I know. And now I'm having trouble hitting my eraser. There's my eraser. Oh, I ruined my drawing. Pity. Okay, what was this now? This is up, up. Okay, this one's up. Oh, sorry, shoot. Down, up. Okay. Just carve that out. Gosh. There we go. All right, so there we go. So at the top here we have 6 nodes, 100% anti-bonding, very high energy. That's like me pumping the jump rope really hard. Very high energy state, right? You're going to be sweating it out doing that. 4 nodes, a little bit lower energy, but still higher in energy, more anti-bonding than bonding character, right? And then 2 nodes, more bonding than anti-bonding character, but not the most stable, which is at the bottom, which is these, single, lazy, jump rope, stable, pi bond. All right, so why did I just do that to you? And what this is going to demonstrate is that in this particular benzene system, we have what we call the HOMO and the LUMO. And you should have noticed that these two node molecular orbitals have 4 more of these pi electrons, okay? So we would call those the highest occupied molecular orbital. In this case, we could say it's the HOMOs because they're the same energy, okay? So in benzene, we basically have these two node orbitals, okay? And then we have the lowest unoccupied molecular orbital, okay? And the lowest unoccupied molecular orbital in benzene are those 2 4-node orbitals, okay? So how does this connect to spectroscopy? Well, it turns out that when you want to go from that, like I say, when you want to do this pi, mainly a bond for that's mainly has pi bonding or character, and then you want to excite that with light, and it goes to from this state here to the next available. The next available from the highest occupied molecular orbital is the lowest unoccupied. And so if you know energetically from your quantum mechanical calculations, the gap between the two, that energy gap, we call the band gap, is going to tell you when you use your fancy equation for converting energy back to light wavelengths. You can use that then to determine what frequency of light should be absorbed. So the band gap, like I said, let's just take benzene here for example. So benzene, we have these configurations. We have 0 nodes, 2, 4, 6 nodes. Our electrons reside here, and this is our band gap. This is this energy required to excite these pi electrons. Okay, so the size of the band gap will tell you the wavelength. Okay, so big band gap. Where's big band gap going to be on the UV vis spectrum? Is it going to be closer to the violet or closer to the red? Yeah, big band gap closer to the violet. A small band gap closer to the red. Okay. So people say blue and red. They don't say violet. All right. So yeah, I mean, it's as the molecular system, as the molecular system's conjugated pi system, okay, increases in size, what happens? The HOMO-LUMO band gap shrinks in size. So that's why, when you need to basically have many ethylenes sort of chained together to make something like beta-carotene or lycopene or one of these in order to get a band gap that's compatible with visible light. Otherwise, you just have a molecule that does well absorbing UV. That's why in organic chemistry you'll do your syntheses of making smaller molecules and you shine UV light on them and you can see them. Okay, but generally they're colorless for many of the organic molecules we make. Okay, and so here, I forget what I want to say here. I meant to have this. Okay, now I see what's happened. So now let's think about what I just said. So say if I have an ethylene. Say I have this ethylene group, I'm going to represent this in our polymer notation, and I can repeat this many times. Okay? So this is our notation for a conjugated pi system. Okay? And what it will look like in terms of band gap is if I start on one end, okay, there's a dot here in between. So here are my orbitals for my pi, and pi star. And this is when I just have a very simple molecule here like ethylene, okay? And ethylene is a case where n is equal to 1. Then I could have n equals 2, n equals 3, n for very large. And I'll populate, of course, the stable pi bond. When these guys interact with light, you can see I have, in this case, a big band gap. There's a big gap here. And the gap size is shrinking, okay? And now I have a small band gap. So as I increase the size of my molecular system by just daisy chaining together, double bond, single bond repeats, then the band gap has shrunk. And that, let's see. Yeah, I'm going to put a little space in. I forgot to update the notes to what I really wanted to show you. All right. Sorry if you can't do that. So another example of that, we'll do this on a spectrum, is imagine these molecules. Does anybody know naphthalene? Naphthalene is found in people's closets that don't use cedar chips to keep the moths out. It reminds me of how my grandparents' closets smelled as a kid. Mothball smell. Anthracene, if we just take 2 benzene rings and break them together and add a third one. Okay, so naphthalene, 2 benzene rings, anthracene, and then we'll go one more to prove a point. Benzanthracene. Okay, so now we've basically have 2 rings, 3 rings, 4 rings. Okay, so we've increased the size of the pi bonding configuration a slightly different way. It's still all the thinking is sound here. And so now let's think about what our absorbance. This is our UV absorbance spectrum. So UV visible, our UV visible absorbance spectrum, absorbance on the y-axis, and wavelength. Wavelength on in nanometers, let's say, on the x-axis. Some units. So say 200, 300, 400 nanometers. 500 nanometers. Okay, so for the smallest naphthalene guy, you might imagine, smallest naphthalene guy, we'll color code him. We'd expect, it's a small system, it's going to be down in the UV, okay? So its peak is down here in the UV, it might have a few more bumps and so forth, but the major peak, it only has pi electrons, so it has one major peak, is down there in the UV. And then we go up and we find something maybe more blue or anthracene, okay? And anthracene's still pretty doggone ultraviolet, but it's going to be a little more blue shifted, okay? Something like this. So there's anthracene. And then, it's not really green, so don't be confused by the colors I'm using. I'm only trying to use different colors. It's not really going to absorb in the green. But now it's going to shift out just a little bit further, not quite be visible yet, and have a peak here that's shifted over, okay? So you can say that as I increase the size of the molecular system, the spectra, the absorbance maximum shifted to higher wavelengths, okay? All right. So I know I tried to mock up a spectrophotometer really quickly last time, but I figure since it's a lab class, we should have a good sense for what the equipment's doing. Okay. Make sure I have enough time. All right. Okay, so here's your spectrophotometer. You'll have some sort of light source. And light source is going to hit a device that can separate white light, which is all different colors, into individual colors. Okay? So, just mocking this up here. I mean, this isn't real. Something like this. Okay? And these optics are going to, by virtue of the angle and various other things, they can then direct the selected wavelength into what we call guard slits. Okay, so imagine, I don't know, it doesn't look very lined up there. These are guard slits. And guard slits are there to take a fat band of light that may be like, say, 40 nanometers, and then you can basically close down these guard slits and block the edges, and so you're just taking, like, say, 1 or 2 nanometers of that color. Okay? So it gives you finer control. This narrows the band. And this narrow band will then come up to your cuvette, which has your sample in it. You have some sample in there. And let's say your sample is, what would be an exciting thing to have in there? Beta-carotene? Yes. That'd be exciting. There's beta-carotene. Oh, beta-carotene. And because, this blue photon is coming in to see beta-carotene, what's beta-carotene going to do to the blue photon? It's going to absorb a lot of it. So I'm drawing a very weak signal coming out. And we have a detector on the other side. Okay? This is our detector. And our detector can do photon counting, or perhaps it can just, it's just a photomultiplier tube. And basically, it can convert photons into a voltage signal. And what it's doing is it's essentially measuring an intensity. Okay? So this is a PMT. Your PMT is measuring intensity. Okay? So what you want to do in an absorbance measurement, absorbance is equal to the log of the intensity initially, before you put the beta-carotene in, over the intensity of, say, the beta-carotene. Okay? So it's a log scale. So if I have 10-fold less intensity, then the absorbance is equal to 1 unit. So if I had 100-fold less, I have 2 units of absorbance. Okay, so it's a log scale. All right, so now we got to crank up clickers. Last clicker question. Please don't come for the last lecture because I'm going to do a review, although it will be a really last-minute review for you all on Friday. I hope you don't wait until the review. Okay. Okay, so this is about bonding and absorbance. Unfortunately, in the prior class, it really wrecked the question. So I got the question formatted so it would fit on the screen. It wasn't fitting on the screen. It's all messed up last class. So which of the following is correct? Obviously, most of these are incorrect concerning molecular orbital theory and UV visible absorbance measurements. Okay, so choice there, choice A, B, C, D. I won't read them. I'll let you read them. But D is kind of hard to read, so I'll read it. Choice D is that the pi star orbitals are out of phase and do not overlap constructively. Okay, everything else you should be able to read. Choose wisely. Some of you have already figured this out. You're clicking in fast. But this is a kind of question you may see on an exam. Okay, decide quickly. People are clicking in really fast now that I'm talking again. Is everyone in? Any last minute clicks? This is your last click. I mean, you know, make it count. Okay, who wants to see the answer? All right, good. Let's see what happens. Let's see if the graph is correct. Oh, look at that, only 64%. Choice D is the correct answer. Fortunately, you guys, most of you got it right. So, two different size band gaps. The larger one is closer to the, not the red end, but to the violet or the blue end. Okay, larger pi conjugate systems have bluer maximum absorbances. That's also wrong. Okay, larger ones would have red color. The LUMO is the lowest unoccupied, not occupied. And D is correct. D is correct. You should, I don't know, there it is. That the antibonding orbitals are out of phase and do not overlap constructively. They're destructive.